Welcome back to the deep dive. We're here to unpack your sources, find those connections, those key ideas. And today we're diving into something that might hit close to home if you're, in college, maybe wading through your math courses. How do these abstract concepts like calculus actually show up in the real world? We've got some material here about analyzing sensor data, specifically soil moisture patterns. So if you're battling differentiation and integration right now, this one's for you.
That's exactly right. Our mission here really is to build that bridge. We want to show you how these mathematical tools, especially integration, are, well, fundamental for seeing the real story. The meaningful long-term patterns hidden inside all that raw sensor data, like soil moisture readings. The aim is to make that link clear, make it concrete, and maybe, just maybe, get you interested in the why behind the math you're learning.
Okay, yeah, let's unpack that. So think about a soil moisture sensor. What does it actually do? It gives you a number, right? Like a percentage maybe,
Right.
but only at a specific single moment. It's a snapshot.
Just one point in time.
And if you have sensors all over a field reading every hour, you just get this flood of numbers.
Discrete data points, is that the term? Measured at separate times. Exactly. Discrete points. You could easily have thousands of these snapshots.
Right.
Over a day, a week, a whole season. But the challenge is, well, if you just stare at one reading or even a long list, it's really hard to see the overall story.
Right.
You don't just want to know the moisture was, say, 35% at 3 p.m. You want the trend. Is it drying out overall? Or maybe how much water has the soil actually gained or lost over the last few days? Are we heading towards drought conditions, looking at the whole week?
Okay, so that's the gap. We have all these tiny snapshots, these discrete points. How do we get from that to understanding the big picture, the trend, that cumulative change over time? What's the heavy lifting involved, mathematically speaking?
Well, this is where calculus really shines. It becomes your superpower, so to speak. You're learning differentiation and integration, right? And they're fundamentally about two sides of the same coin. Rates of change and accumulation over time. Both are useful here. Differentiation, conceptually, helps you figure out the rate the moisture is changing right now. Is it shooting up after rain? Is it slowly dropping in a dry spell? You could maybe figure that rate out by looking at how the readings change from one moment to the next.
Okay. So differentiation is about the speed or the direction of change at a particular point. But then how do we get the total change or the cumulative effect over, say, a whole day or week?
Precisely. That's the job for integration. Integration is the tool that lets us synthesize or accumulate all that information from those countless tiny sensor readings over a period. Think about the definition you're learning the limit of a sum. Conceptually, that's what you're doing. You're adding up tiny bits of change, tiny values, over an interval to get the total picture. With soil moisture, you're using integration to go from single readings to understanding the total water gained during rain, or the total water lost over a dry week. You integrate the rate of change over time to find the total change in moisture. Or sometimes you might integrate the moisture level itself over time.
Why would you do that?
Well, that could tell you something about the cumulative exposure of plants to moisture, which is really useful for things like predicting growth.
Okay, that clicks. So it's kind of like tracking your bank account. Seeing one deposit, that's just a snapshot.
Right.
But if you wanted to know the total change over the month, you'd have to sort of integrate all the pluses and minuses over that time, add the deposits, subtract the withdrawals.
Yeah, that's a great analogy.
Or like if you measured how fast water flowed into a bucket every single minute, that's like the rate maybe linked to differentiation. Then integration is how you'd figure out the total volume of water in the bucket after an hour. You're summing up the little bits.
Exactly. You're building the cumulative picture from the instantaneous pieces.
Right.
You move from discrete points to a continuous understanding over time. And for you, wrestling with calculus problems right now, this is it. This is a direct, really powerful application of what you're learning. It's not just math on a whiteboard. It's actually driving how we analyze data in the real world, in fields you might even work in someday.
So the main takeaway seems to be integration lets us take all that separate sensor data, those snapshots, and move beyond just looking at individual moments. It helps us see the bigger picture, like those long-term soil moisture trends, reveals patterns you just couldn't spot otherwise.
And knowing those patterns is crucial, seriously important. In farming, it helps with efficient watering, predicting crop yields, saving water. In environmental science, it's vital for modeling ecosystems, managing water resources, studying climate change impacts. It turns messy numbers